that because the laptop was taking slightly longer time to load today, I missed recording. So now it is recording. So since we are considering one-dimensional signaling and the noise variance is n0 by 2, so R is a complex number, S1 and S2 are both real numbers. So we deal with the special case where we take only part of R. Fine. So say rather you say we define R prime as R equals S plus right?
So W is the noise.
Yes. Oh,
Sir,
eta. We
uh,
used eta, right? Yes.
yes,
So in
sir.
my papers I use W for noise. So I got
So, but
fine.
since the channel is a real world channel and we are transmitting a real signal, how can the noise be complex?
So Adit, we are dealing with complex baseband. Everything that we are doing is for complex baseband equivalents. You remember that we received a time signal ST and we converted everything to complex numbers, or we converted everything to a complex vector.
Yes, sir. Okay.
Fine. So we started off with a waveform and then we said that we want to convert everything to a complex vector. So since in the present case, so this R prime equals this, so real part of eta or eta prime is because eta we know is right, and we discussed circular symmetry in the previous semester.
Yes, sir.
So from that definition of circular symmetry, we say that the real and the imaginary part will both be identically distributed and have variance n naught by 2. So that fine. Makes sense, guys. So R
Sir,
prime,
sir, you repeat
yeah,
it once again.
yes. So you remember we discussed something called circular symmetry in the previous semester.
Okay.
So what that said was basically if there is a circular symmetric random variable, then circularly symmetric random variable, then so if Z is circularly symmetric, sigma square, then for Z equals this.
Yeah, sir.
Yeah, so because of this, if we consider R prime as real part of R, we can write S plus real part of eta.
So between like why there is no like why we are considering SS to be real? Like what is the reason?
See, we defined S as plus and this thing.
Okay, okay.
This is
Yes.
real, right?
Yeah, yeah, fine then.
So this is a special binary antipodal. This is a special case that we are talking about. This is the example case that we are building on. After I
Okay.
finished yesterday's lecture, I realized that I haven't discussed this in as much detail as it should, as it deserves. So that's why I'm redoing this in greater detail. So this is fine.
Okay, sir.
Now this R is R prime is something like this. This is R prime. So these are two symbols that we sent, and this is R prime. Now what we want to do with R, since we have already talked about decision regions. Talked about see that right. Kirti, please mute yourself. Just want to ask something. Yeah.
Sorry.
No, no issues. Yeah. So this is right.
Yes, sir.
Yes. So, and from what we have discussed earlier, maybe what you can do is you can gloss over the last 15 minutes of yesterday's lecture. This is the same thing, just in proper detail. And from what we have discussed earlier, we want a mapping of R, G of R actually, such that G of R maps the real line to right. Fine.
Yes, sir.
And scene decision regions. We have seen the definition of decision regions. Now, so letting D1 be the region corresponding to D1 equals R such that P times, yeah, right? This we had started off and this we had derived in terms of the Euclidean distance.
Yes, sir. Yeah.
Mm. Mm. Equivalently are such that R minus S1 minus Xi1 is less than I'll substitute actually S1 and S2. What I'll do is plus this goes away, right? Agreed?
Yes, sir.
So now I'll just do some calculations because whatever we have done already is for complex numbers or for complex distributions. For real distributions, it becomes slightly different or slightly easier. So let's calculate f r given es equals 2 pi. So again, root over pi and not, because the variance is e to the minus x minus root over es. So this becomes, so this thing will disappear, and so p times this is p times this. So natural log p natural log of, or rather p by 2 natural log of p by 2, or yeah, p plus half natural log of pi n naught minus
Log P, right?
yeah log p. Fine.
Yes, sir.
So
So how do we know that it is a Gaussian? Like
that we
it's
started off with
AWG
Gaussian.
because it's
Sorry.
AWG because it's
Yeah, we
AWG.
started off with Gaussian noise. We showed that. So we actually did that little trickery where we showed that correlating this noise or passing this noise through a correlator is equivalent to passing this through a filter, and since filtering a Gaussian process results in a Gaussian process, you remember that trickery?
Yes, sir, we got some.
Yeah, so filtering a Gaussian process results in a Gaussian process, and this is one sample of a Gaussian process, and so we need to do some trickery to, or we need to resort to some tricks to prove this, but Yes, so the laptop has frozen. Give it a moment.
Sir, minus half ln pi n, no?
So, yeah, so half log. So this is multiplying. I'm taking the log of the entire thing. So then I'll take the minus sign. Minus sign is the next step. This is OneNote has frozen. So waking up. Waking up. Waking up. So there is something else you guys want to discuss while the laptop is misbehaving?
Sir, can I clarify something here in this in
Yeah,
between
sure,
time?
shoot. I
So
mean, while
basically,
the
what in this binary pattern, like what we are doing is we are transmitting only two symbols. Like one is
yes,
S1, another is S2,
yes,
and here you have mentioned it as root epsilon s. Like it is like a binary. Like what does root epsilon s means? It's like plus or minus some
energy.
voltage.
And that's not epsilon. That is
Yes.
a cursive E
Okay.
one.
ES is fine. Like I'll go with
Yeah,
this.
cursive E time or ES. So that is the symbol energy
Okay, so you are saying you are transmitting a signal of energy root ES.
of energy ES.
Sorry, of energy ES. Okay, you did you mention what type of signal is that?
I said that it's a binary antipodal, so BPSK
Okay,
in
PPSK.
simpler words.
Okay, then in between step, like right now you wrote that R minus S1 square minus epsilon, like D1 is equal to given. It is the same thing which we derived before, right? That nearest one, like
Yes,
nearest
it
one,
is the same thing, just that just in order to
innovation,
be
innovation. This
no,
thing is
not
there.
not innovation. So just
Epsilon
in
one is
order
there,
to
right?
be what do you say, complete, or just for the sake of completeness, we are doing this again. This won't take much time, or this shouldn't have taken much time had OneNote not crashed. So, okay, the application is not responding. The program may end process, I believe. I don't know what process will it end. It seems that even Teams has died. So it's still sharing the screen. Ah. So 5-minute break, guys, while I try to mend this thing.
Yes, sir.
So, so timeout. That's all I can say. Why is this still sharing the screen with all this embarrassment? So OneNote has started. Teams is yet to start. Teams is also starting. So we lost 10 minutes, right? Do you have a class at 4? Guys?
No, sir.
Okay, so we'll cover up these 10 minutes over there. Teams is starting. We ran into a problem. Try again in a few minutes. Yes. You can see the screen now. We lost
Yes, sir.
maybe the last 3 or 4 minutes of writing. So P, what I was saying was that right, and right.
So minus half because under root pi and naught was in denominator.
Oh yeah, minus half. Fine.
Yes, sir.
So similarly, the other one becomes right. So what I wanted was xi1 now. So this part this cancels out. Xi1 is n naught natural log of p. Xi2 is n naught right.
Yes, sir.
Yes. Then d1 equals r such that r minus root over es whole square minus xi1 is less than r plus root over es square. Right?
So how did you conclude that epsilon 1 and epsilon 2 to be this thing, sir?
Sorry?
How did you this epsilon 1 and epsilon 2 to be n not ln p and n naught?
So this is not epsilon, this is xi
Okay, so psi.
1.
Sorry, sir. Confusion with this
And
thing.
this is from the previous lecture where we derived d1 and d where we derived dn. So I
Okay, sir.
just
Yeah.
wanted to confirm I just wanted to confirm my expressions for xi1 and xi2 because yesterday while doing this quickly, I had taken these to be n naught by 2 natural log of p and n naught by 2 natural log of 1 minus p, right? If you look at yesterday's notes. So I did this quickly and I made that mistake.
Okay, sir.
So today, just to be double sure, I derived it out. Since we are doing this thing in detail, so let's spend some extra time on that. So that's what I did. And yes, so this equals r such that r square plus es minus 2r es minus xi1 less than r square plus es plus 2r root over es right. So r square cancel out from either side. Es cancels out. Right. So r such that minus 4r root over es is less than xi1 minus xi2 because we got 8 instead of 4 yesterday. That was another reason. So r such that four r yes so when I take minus on both sides, this becomes xi2 minus xi1.
Yes.
Right.
Yes, sir. Yes.
So because of that, this so or r such that r is greater than this beast. Fine. So, oh, sorry. D1, D2 automatically becomes right.
Yes, sir.
So, so let me call this quantity as lambda threshold. Then, so I'll draw that line again. This line, this minus root over es, es. Okay, this is what we get. And this, it'll change all the colors and then get back to black automatically. This and So this is the threshold lambda. Fine. So we simply declare that we sent S1 if R is greater than lambda, sent S2 if R is less than lambda. Fine. Detection estimation, people remember anything like this? This is like a binary hypothesis test.
Yes, sir.
Yeah, so this is like a binary hypothesis test. And so now the question is that this lambda is a function of the prior one. This is a function of the prior probabilities. And so if what happens is that basically, again, I'll draw this line, this. And if we considered one case yesterday, P equals 1 minus P equals half, then lambda equals 0. This we considered yesterday. This is
Yes.
lambda.
Yes.
If P
Sir,
greater than 1. Yeah.
sir, how is it different from what you taught in the last semester during the last section of the course?
So there we didn't go in this much detail.
Okay, means the results are almost matching.
Yeah, I agree. This is so um, more than that. So this is the results are exactly the same.
Yes, sir.
Science does not change with detail.
Yeah, yeah.
So you were taught Ohm's law. When were you first taught Ohm's law?
Fifth or sixth class.
Fifth or
Yeah, yeah,
sixth or
got it.
maybe class 9, I believe.
Yeah, I don't remember exactly.
Yeah. So and how many times after that have you been taught Ohm's law?
Okay, many times.
Has the Ohm's law changed?
No, not changed.
So similarly, we didn't go see, we didn't cover this much detail. Last time what we did was we simply said that we want to have a threshold. We didn't discuss about signal spaces. We didn't discuss about correlation receiver. We didn't discuss that for optimal detection, we need to divide everything into decision regions.
Yes, sir, got it. Thank you.
Yeah. So this is just more. So I said this in the previous semester itself. I believe that we'll spend half the semester next time just over these two classes. So yeah. So this is for. Oh, now it has turned red. Nice. So if P is greater than 1 minus P, lambda equals. So if P is greater than 1 minus P, lambda is less than 0. Right? P is so P is greater than 1 minus P. This fraction, oh, this fraction is less than 1.
Yes, sir. Got it.
Since this fraction is less than 1, lambda turns negative. So I can draw another line here. this, and let's try green. If let's try some thinner green. P is less than 1 minus P. Lambda is greater than 0, which is but obvious. And again, it is obvious that as oh sorry, P is less than 1 minus P. As the ratio between P and 1 minus P will increase, or as the ratio of P and 1 minus P will increase, this lambda will also increase. Fine. Right?
Yes, yes, sir.
So what does it mean? It means that as the prior probability of transmitting one out of the two signals is increasing, we are increasing the possible region right. This is what we are doing. So
Yes,
the
sir.
higher the prior probability, the more is the region in which we expect that signal.
Yes, sir.
So this is the or this is what so change lambda and the detection threshold changes, but and as P or 1 minus P go to 0 and 1, or as P goes to 0 or 1, the threshold will change to minus infinity or infinity. You agree on that?
Yes.
So this is basically the idea behind, or this is how we divide the entire space into decision regions. So once we have decision regions, the next step is to obtain now m equal to 1 to capital M Pm summation m prime not equal to m equal to 1 to capital M prime equal to 1 to capital M. This beast. But in the present antipodal case, right? So probability of error equals for m equal to 1, P or summation. So P. So let's write out the summation because we just have two cases. P. So this inner summation will be just over m prime or will be just over one entry because it'll either be D1 or D2. So probability that S1 is transmitted and it is detected as S2. So R given S1 dr plus 1 minus P integral over d1 S2 right.
Yes, sir.
So let's first evaluate this. This means lambda to infinity. Sorry, d2 is minus infinity to lambda, right? Minus infinity to lambda root over pi and naught. R minus es by n naught. Fine. This times P. Agreed?
The square term on e power r minus
Sorry, the what?
square, the square on r minus root of
Yeah, there's a
es.
square term. Yeah, typo. Yeah, this is right.
Yes.
So
Yes, sir.
right. Sorry, q of say q of t. So I'll write it again. Q of x equals x to infinity 1 upon root pi. This. This we did in the last semester. Or this we defined in the last semester. Again, as Vishal kindly mentioned in the last two lectures.
Yes, sir.
Yes.
So this is p times, actually, since there's a p here. So this is p times this. And similarly, d1 given fine. And Okay. Fine.
So why Q doesn't have any R terms? Sir? Like we have considered P into Q of something, right? Like R term, like
Oh,
why do
sorry. One step I forgot. So this is I gave the final result after skipping a step. So this gives you Q of lambda by root over n naught plus 1 minus p es plus lambda root over n naught and so this is the probability of error for p equals 1 minus p equals half. Pe equals Q of Es by n naught. Right? This was the
Yes, sir.
correct expression. I just somehow, yeah. So note that this is if the real valued component of noise has a variance n naught by 2, or the complex noise has variance n naught. In case you are given that the real noise added to the system, the has then right. So this makes sense. You don't rely on the formula. You look at the statement properly. The noise can be real valued. The noise can be complex valued. So if you are dealing with real valued noise with a given variance, then you reduce it to this expression. Similarly, if you are given that if you're what we have done is for complex valued noise having this variance, but if you are dealing with real valued noise having a given variance, then the final expression changes, but the steps remain the same.
Sir,
Fine? Yeah, Adit.
sir, I am still seeing the last statement that I am seeing is P is equal to Q bracket under root 2 EB by N naught. Is
Yeah,
that what you wrote?
that is still the last statement.
Oh, okay, okay.
Okay, so you see that the first statement root EB by N naught, this is when you are given the variance of complex noise, or N naught. This you have to keep in mind. The variance of complex valued noise, and we take only the real part. This is the case variance of the real valued. So everything else remains the same. All the steps will remain the same, just that so don't blindly trust a formula. Fine.
Okay, sir.
So yes. Now let us yeah, let us extend this to a slightly more general case. So now instead of binary antipodal signaling, let the points be general points given by, or let the points corresponding to these be given by A and B, and the variance of the, so let the variance remain the same. Let's not change the noise variance. Fine. So what we have now is that A, B, and again you get similar points. You have to determine this threshold lambda.
Yes.
Yes. So in that case, for symbols lambda equals fine. I'm just stating this as a result. You can go back here, do all this jugglery, because now this jugglery will involve so now this jugglery will involve
Sir,
actually in, yeah, yeah, keep.
so can we say that like if A and B are there and if they are not equal for one also we could like we
So
got a lambda before, right? It will be shifted by A plus B by 2. Shall we say that?
yes, you can say that it will be shifted by A plus B by 2.
Just an offset of A plus B by 2 in the additional formula we'll be able to get for this.
Yeah, but that's not simply not the means that is one thing that so what you are doing is that actually I could have done this for a general AB, and that would have made things a lot more messier. But the point here is not that. The point here is that this, and so lambda, the optimal lambda is a plus b by 2, that you can obtain by doing all those tricks. The point that I want to emphasize over here is that in that case, what happens is that yeah. So if R given A is right, these will be there.
Yes, sir.
Then you can show that. So actually using the ideas above, I'm simply going to write the result. Actually, I'll do 2 steps. So sorry, b minus, since b will be bigger. This fine. From what we did with the Q function above, makes some sense. Okay, makes less sense. So we will pick up here tomorrow then, if it has stopped making sense.
Okay, sir.
Okay.
Fine, great. Sorry for the sorry for the laptop troubles. I profusely apologize, but this is something that I cannot help. Yeah. Bye. Have a nice day, all of you.
Sir, could
Bye,
you
sir.
share notes as well?
Today's notes.
Yes, sir.
Yeah, that I will do. I shared yesterday's notes, right? Yeah, lecture 14 is shared.
Okay, sir. Okay, sir.
Yeah, lecture 15 I'll share, and the videos I will download and then share. Okay. Bye.
Thank you, sir.
Thank you, sir.